Mr. Strauss is filmed before a live studio audience. No laugh track has been involved in any way, shape, or form. All right, so 2, 4, 6. 1, 2, 3, 4, 5, 6. We will need how many more electrons, Nikki?
8. I mean, 2.
2 more for a total of 8. 2 bonds. Now, sulfur is also in the oxygen family. And so it starts off the same way. And when I excite my electrons, same thing is going to happen. I'll end up with sp3 hybridization. And I will need 2 more electrons for a total of 8. So oxygen and sulfur, those two things behave the same way because they're in the same family. Which I think is kind of an interesting aside here, Tyson. All living things require what compound?
Carbon.
Water.
Water. Most living things require oxygen, but not all of them. Everything requires water, which is H2O. Oxygen, also very important. Now, there are some creatures, bacteria, down on the thermal vents underwater, under the ocean, that use not H2O or O2, they use sulfur as their power source. Sulfur is in the same family as oxygen. They use H2S, not H2O. And so H2S is a very strong acid, but the bacteria thrive on it. And so, Alice, and some science fiction writers envision planets where life is not based on H2O, but life is based on H2S. Instead of having water flow through your veins, Mariah, you'd have H2S flowing through your veins. You'd have like acid coursing through your veins.
Possible.
Maybe I must have took chemistry.
That's right. So that's why you all understand the movie Alien vs. Predator so much better now.
Oh, really?
I've never seen that movie.
Good.
It's a creepy movie.
There you go.
What?
It should have split acid. Alien split acid.
So H2S.
Right, H2S. All right, so sulfur, though, because there's the d orbital, has another option. It can kick the electron up into the d level.
Why sulfur though? Because that's just so it's not that energy.
Because sulfur's in the third energy level. You won't be confused long. How many s orbitals did I circle there, B?
1,
Okay. How many p's did I circle?
3,
And how many d's did I circle?
2.
So it's sp3d2 hybridization. And in total, I circled 6 lines. So I draw 1, 2, 3, 4, 5, 6 lines with 1 electron in each. So that means I'm going to need 6 more electrons for a total of 12.
Did you do the right there?
What's
3
wrong?
lines for D.
There are
So you need
4
6
lines
lines.
for...
No, for D.
Because you figured
That's
it out
right.
from the...
Oh, sure, yeah, we should draw in the extra Ds. So we have 3, we have Ds left over, 3 of them.
Do we have to draw them?
No, but it'd be a good idea. So with fluorine, we start off with 7 valence electrons. If I excite one up, I still have 1 electron that is unpaired. So when I hybridize, I'll end up with sp3 hybridization. I'll need 1 more electron for 1 bond for a total of 8. So fluorine, 1 bond, 8 electrons. Chlorine is in the fluorine family. And so the same thing happens. I can excite my electron. I circle those to hybridize. And I end up with sp3 hybridization. I draw in 4 lines. No, 4 lines, but how many electrons? 7. So I'll need 1 more electron for 1 bond and 8 electrons.
Does it matter you put the dotted one?
Wherever the unpaired one is. So there's 1 electron that doesn't have a friend.
Just
Yeah,
leave
but
it
could
like
you
that,
put that in
right?
the first one? Like,
Yeah, you could.
Couldn't you just leave it like that though, without having a-
Yeah. So fluorine will evade with 1 bond, chlorine will evade with 1 bond, but Jordan, because there's the 3rd energy level, I could kick my electrons up into the D.
Why would you do all three?
I kick all 3 electrons up into the D,
No, why?
because I can. You wanna
Can you
unpair
just
them?
get two?
No, not really.
Well, tell me why.
Because it's more energetically favorable to have them all unpaired. So Hannah, what's my hybridization?
It's gonna be SP3, D3,
Okay, and how many lines should I draw?
7,
7.
and they're each gonna have 1 on.
And so I'm gonna need a total of 7 bonds, 14 electrons. Sabah?
See, we
Trillium. Yep.
So in the movie Alien vs. Predators, who's the aliens and who's the predators?
The aliens are the lizard thingies and the predators are the predator thingies.
Because aren't there people in that movie or no?
Ones that the
I never saw the
I
movie.
know.
Oh,
I saw the first one.
It's all a new one.
The first one was back in the day when I was a teenager, so that tells you how old that
Black
movie
and
is.
white.
All right. So today's objectives are to label the parts of a double and triple bond and explain how the properties of single, double, and triple bonds differ and why.
You never did phosphorus. Yeah.
Oh, did I forget one?
Yeah, phosphorus.
Oh, I'm sorry. I got so excited I thought we were done.
Are you checking off this homework?
No, because the lab is gonna be so long and so encompassing and it's gonna have this on there, that I'm just gonna check the lab. This is like the practice round.
This should be checked, then you can help us. Yeah.
So, with phosphorus, I can kick that 1 electron up. sp3 hybridization. I'll need 3 more electrons for a total of 8. But because phosphorus is in the 3rd energy level, Zane, I could kick that electron up to the D. And what type of hybridization would I get, Zane? How many s orbitals did I circle?
3, 5, 1,
How many p's did I circle?
3,
How many d's?
1.
So it's gonna be sp3d hybridization. How many orbitals did I circle in total there, Lily?
5.
5, so I get 5 lines. 1 with each electron in it. I'm gonna need 5 more bonds for a total of 10 electrons. Yep, Allison.
Like on the top one, you have a number of bonds, do you always put how many more bonds that you're needing, or?
How many that you need? What? 1, 2, 3, that's the number of bonds that I'll need. That's a pair that came from the phosphorus itself. So it's not getting it from somebody else, so it's not bonding. You could say that's a non-bonding pair.
And then the electrons is always the total,
Always the
not how
total.
many.
That's what I'm gonna ask for, is the total, not how many you want. Any other questions? All right, so let's start with our objectives today, and that is to label the parts of double and triple bond.
We aren't doing hybrid.
That's what we're doing. So the fifth type is a hybrid and a hybrid overlap. And one example of a hybrid overlap is a double and a triple bond. And so in this example, we're going to explain how double and triple bonds work. You read about them last night in the reading. Now I know from previous experience that reading gives people trouble. So that's why I had you read it first, and now hopefully I'm going to explain what you read about last night. So the example, the classic example of a double bond is C2H4. Now how do I know there's a double bond there? Well, you don't know from just looking at it like that. You have to do the Lewis dot structure. So carbon, got 4 valence electrons. I'm going to have to form a double bond between the 2 carbons and a single bond between my hydrogens. And so this way I can get 8 around the carbons and 2 around the hydrogens. So I end up with a double bond between those 2 carbons. So while you copy that down, I'm going to submit appendix.
Wait, were the 1 and 2 just the objectives up there, or are they rules?
Those are objectives. Ryan's not here. All right, so we have 6 atoms here, Katie. So when we draw this, we're going to need 6 sets of axes. That's going to get very ugly. So we're not going to draw all 6 sets of axes. We're just going to look at those 2 carbons. Okay? Because it's a lot easier to draw.
So this, you know, is a double bond.
So we're just going to look at the double bond. We're going to ignore the hydrogens. Carbon starts off as S2P2. And then I'm going to excite my electron up. And now when I hybridize, I'm not gonna circle all the orbitals. I'm only going to circle one of the S and two of the P's. One S and the two P's. I'm gonna leave that P orbital alone, because I'm gonna need that P orbital to do something else. So, I'm gonna hybridize now, and I'll end up with sp3 hybridization. Yes, Nikki?
Are we always just gonna leave one out, or will it?
When you do a double bond, you're always gonna leave one p orbital alone. Oh, shoot. No, me too. Big mistake. Thank you for catching that. Yes, Hannah?
How can you tell the difference between a hybrid and a hybrid and a hybrid and an X or a hybrid?
Because, and for you guys, it'd be pretty tough, because you haven't had a lot of experience. But normally, if you see something like hydrogen or a halogen, if you see hydrogen, it's gonna be an S, or an alkali, because they're all ending in S1. If it's a halogen bonding, it'll be a P overlapping
I'm
with the
just saying,
hybrid.
like on our chest, like how are we gonna?
I don't wanna actually put that on the test.
Okay.
We really focus on this, number 5 on the test. I'm gonna ask you to draw a double bond or a triple bond.
You don't even do like S plus P.
So it'll specify which one we have to do.
Yep, it'll be a double or a triple. Okay, so since 2 p orbitals and 1 s, I draw 3 lines. I have my leftover p. And do you remember what an sp2 hybrid looks like?
Yeah.
Yeah.
What does it look like?
Is it kidney beans or?
Kidney bean with a piece of corn. So here's the sp2.
And there's
sp2 hybrid orbitals. They look like a kidney bean with a piece of corn, and there's 3 of them, all 120 degrees from each other. And each carbon is doing this. So each carbon has 3 of these. So I'm going to draw the bonding between those 2 carbons. The book showed this in a picture last night when you read it. We're going to look at the bonding between the 2 carbons, so we're going to draw 2 sets of axes. One carbon is here, 1 carbon is there. And each of them has 3 kidney beans around it. 1 kidney bean is going this way. And that kidney bean is sp2 hybridization. Now the other 2 kidney beans, we're not going to draw in. One of them is coming out of the board at you, bonding with that hydrogen, and the other one is going into the board, away from you, bonding with that hydrogen. We're not gonna draw them in, it just gets way too messy. This carbon also has 3 kidney beans going around it. One of them is going this way. They're supposed to be the same size, yeah. And they share 2 electrons. So you have 2 sp2 orbitals overlapping. There's an sp2, there's an sp2. 2 hybrids. 2 hybrids overlapping. That overlap is a sigma bond. So here's an example of 2 hybrids overlapping to form a bond. And they form a sigma bond, which is the first bond between the 2.
There's 2, right?
Now we still have to get the double bond. All we did was make the first bond. Now how do we get that double bond? Well, that's why we left that p orbital alone. That leftover p orbital is on the z-axis.
Do you guys see what that one is?
Yep. So that p orbital is on the z-axis, 1 lobe above, 1 lobe below. And the same thing is happening on the other carbon.
On the test, can you do a pencil?
You can do it in pencil, sure. Now, these p orbitals each have 1 electron in it. So, yeah, you noticed it, didn't you, Luke? You know what they're gonna do, don't you? They each have an electron in it. They say, hey, let's share. And so the p orbitals are going to share their electrons, and the p orbitals are going to overlap. And they're going to form a ring. And this is what you read about last night.
Bottom and top?
Bottom and top. You have a ring like this. And that whole blue thing represents the second bond to create the double bond. And what shall we call it? Pi. I just found out who read the book last night.
Not as, yeah.
So, an overlap of p orbitals is called a pi bond. Okay? So, in summary, a double bond has sp2 hybridization. It always has sp2 hybridization, except for that exception that I won't tell you about until later. So it always has sp2 hybridization. It always has 1 sigma and 1 pi.
What's that sigma?
Sigma's right there. Overlap
But
of
you have
those
a
two.
different sign for sigma.
That's sigma.
Oh, just
That's
for the
pi.
skinny, okay, just,
One sigma bond, right?
Does that bother you? Should I write it better?
yeah.
There you go. 1 sigma and 1 pi bond. Gives you a double. So any questions on how to draw a double bond?
Are we going to do that on the test?
You either are gonna have to draw the double or the triple.
There's another one.
So our last example, Allison, is the triple.
Easy.
You ready for it?
Not really.
Okay, let's do it. So the example, the last example, would be of a triple bond, and the example we're gonna do is C2H2. How do I know there's a triple bond? Well, you really don't unless you do the Lewis dot structure. So my carbon is looking to have 8 electrons. So the only way you can do that is by putting in a triple bond.
What's our test on again?
Lewis dot structures, hybridization, and what we're gonna learn tomorrow. Vesper theory.
Reason for my lab.
Yeah, that's how you're gonna learn Vesper theory, is by doing it. By building the models, that's the best way to learn it. Is to sit down and actually, because in the reading last night, there were pictures of all that stuff, right? So the best way to learn those pictures is to build them. No, it stands for carbon. Just like last time, we're going to ignore the hydrogens, we're gonna focus on the 2 carbons. The electron gets excited and goes up into the P. Now I'm gonna hybridize. You bet. Sometimes this chemistry gets me excited.
Funny.
Sometimes.
We've been waiting for that one all day.
What?
Is this supposed to be a joke?
No. Joke is, Forrest walks into the bar, Bartram says, "Why the long face?" That's a joke.
What?
That's the no laughing.
Maybe I should add a laugh track. All right. So, the electron jumps up, but when I form a triple bond, I'm only going to hybridize 1s and 1p. And again, that's something you just memorized. When you have a triple bond, it's just an s and a p hybridized.
So the more bonds there are, the less you hybridize?
No, it's more a matter of, it's just one of those things you just memorize. Triple bonds, sp hybridization. Yep, Lily.
Is there such thing as a quadruple bond?
There is no such thing as a quadruple bond. Triple is the highest you can get. So after the hybridization, I have 2 sps and my 2 leftover p orbitals. And the sps,
Don't you have to put P2?
no.
No, answer with 1P. No, but I'm saying up on top.
No,
No.
just If you wanna put the energy level, you can, but you don't put the number of electrons.
Okay.
Not for molecular orbitals. And sp orbitals look like kidney beans and corn, just like the last one. There'll be 2 of them for each carbon.
Don't they have the same as what you just did?
That's what I said, kidney bean and corn. One will face this way, one will face that way.
It's basically a circle.
So let's draw how this bonding is going to work. One carbon is here, one carbon is there.
I think there's 3 bonds, don't you need a third one or no?
Yep, we're going to need a third one.
Third axis?
Oh, no. There are 4 atoms, so I'd have to draw 4 axes, but we're leaving the hydrogens off. So the first thing is the bond between the 2 sp orbitals. SPs are kidney beans. And then the other sp that's forming the first bond is on this carbon, and it's facing the other way. Now remember, each carbon has 2 kidney beans, okay? One facing that way, one facing that way. But I'm only drawing the ones that are facing this way and bonding. I'm not drawing the kidney beans that are facing away. Each one has 2 kidney beans. The overlap of those 2 electrons forms our first bond.
So really there should be, like, more than, there should be 4 kidney beans up there, but there's one.
Right, there should be 4. There should be another kidney bean here and another kidney bean there. But we're not drawing them in because they're not involved in the bonding with the carbon. So what should we call that overlap? What do you think, Ashley? Sounds good to me. Sigma bond. Now how do we get those other 2 bonds? Same way we did with the double. We've got our p orbitals just like with the double bond, we've got those p orbitals. They each have an electron in them. And those p orbitals overlap.
There's a picture of this. There's a good one.
Yeah, the book.
No, on your, right there.
No.
Yes.
So we've got an overlap, it forms a ring, just like we do with the double bond. What do you think we should call that, Brad? Pi bond. That gives us the second bond in there.
It's the same exact thing, except what we just did.
But it's triple bond.
But it's a triple bond, right? So what we need to do is to draw in the third bond, the triple bond. Don't forget, we had another p orbital, right? We had two p orbitals with one electron in it. So that third p orbital is on the y-axis.
Wait, how do we, what do you mean with
Should this just look like a blob by now?
Yeah, mine does. It should look like.
My color
Love
coded, color coordinated mine, so it doesn't look that bad.
Where's your color coordinated? Oh, this one.
So those p orbitals are on the y-axis, and they overlap just like the ones on the z did. They're going to form two interlocking rings. The green one like this, and the blue one like this.
Well, is the blue one under the green one? Yeah.
Um,
Doesn't
no, it's above it. And then I attach these.
You said it was above.
This one is above here, it's below it in the back. So I have two interlocking rings.
There's electrons in the balloon, right?
Yep. So there's two electrons in there. And the name of that is pi bond.
Wait, is it just
So
like right
just
there?
like two.
Nope, the whole blue thing, that whole blue ring, that's one pi bond. That's a very good question to ask. The whole green thing is one pi bond. The whole blue thing is one pi bond.
Is it also,
Please raise your hand, one question at a time. Yep, B.
is the blue one also a p orbital?
Yes, the blue one is also caused by an overlap of p orbitals. So, to summarize, a triple bond is caused by an sp-sp overlap. So a triple bond always has sp hybridization, always. How many sigma bonds do we have? One. And how many pi bonds do we have? Two. So a triple bond is always one sigma and two pi's. So in the short amount of time I have left, let's talk very briefly about the properties of single, double, and triple bonds. So we can draw them, that's great. But really what's more important is to be able to say, okay, this thing, this compound's got a triple bond, how is it going to behave? This thing is a double bond, how will it behave? And tomorrow I'll talk very briefly about something very new called graphene, which utilizes double bonds to be an excellent conductor. which might be replacing all of our copper wires and might be key to harnessing solar power. So, properties of single bonds is that they are weak bonds. They are long, relatively long bonds, and they can rotate.
They do rotate or they can
They
rotate?
can rotate. Oh, you're saying like, yes, and they do rotate as well. They
Like
can,
all, like constantly?
yes. So like, here's a molecule that has all single bonds. The bonds are actually quite long, and these bonds will rotate.
Oh,
A little too much there. So as this molecule is going through space, it's rotating. So this molecule is the same thing as this molecule, C2H2. It's just rotating like this. Okay. Now if you throw a double bond in there, you lock the molecule into position, meaning that with a double bond, you can no longer rotate. So the molecule will have to pick, either I will be like this with both my, just kidding, atoms down, or I will have to lock into position with one down and one up. And they will have different properties and behave differently.
Can you both up?
Sure,
it's like, is it like the same?
because they rotate. No, that's good to, we forget that these things are always moving. So tomorrow we'll finish summarizing the bonds. No homework tonight. Thank you very much for your help. You can pause it now.